Okay, so our aim here in this section, of course, ultimately is to prove that the set of rational numbers is countable, and we are heading towards that goal. And in that direction, we now need this technical lemma. Here we have a set A, which you can see from the definition that it is a subset of this Cartesian product of two copies of the set of natural numbers. And what is this subset? It is the set of all ordered pairs of natural numbers where the coordinates satisfy these inequalities. That is, the second coordinate is less than or equal to the first coordinate, and both of them, of course, are greater than or equal to 0. This in fact need not even be mentioned, and we have to prove that this set is countable. That means this set itself has a bijection with the set of natural numbers. So let's see how the author has proved it. Now the proof starts off with a sequence of natural numbers whose definition is recursive. We define a sequence an of natural numbers recursively by setting a not equal to 0. So the first term we are defining to be equal to 0. The first term is 0, and the term n plus 1th term an plus 1 is defined to be equal to an plus n plus 1. Now simply as saying that this is a sequence of natural numbers is in fact, strictly speaking, it has to be proved, but the proof is almost trivial because the definition is recursive and the claim is about natural numbers. So naturally you can prove this claim by induction. What is our claim? That this is actually a sequence of natural numbers, that is, all its terms, all the an are in fact in the set of natural numbers, which you can prove by induction pretty easily and in a straightforward manner. You apply induction on n. A naught is 0, which is natural number, so that gives you a basis for your induction. Then you assume that an is a natural number, that is your induction hypothesis for some natural number n. But then from this formula you can clearly see that an plus 1 is also a natural number. So by induction, this in fact is a sequence of natural numbers. Not necessarily the sequence of all natural numbers, but a sequence of natural numbers. All its terms are natural numbers. But now we are in fact interested in something else about this sequence which will be helpful to us. In the proof that we are going to do. This is only the beginning, and that thing is that this is not just simply a sequence of natural numbers, but it is strictly increasing. Okay, that we now have to prove. We now show that an is strictly increasing. If you somehow suddenly think that any sequence of natural numbers is strictly increasing, that is not true. You can consider the constant sequence, all of those terms are 1, 1, 1, 1, and that is not strictly increasing. And by strictly increasing, we of course mean this, i.e. an is strictly greater than am whenever n and m are coming from n and n is greater than m. Now this claim is not proved in the text because it is supposed to be something very straightforward, but we do it here. Okay, either we have to do it here, we are not allowed, I mean, at least that's how I feel, we should not allow any gaps in whatever we have to show, no matter how trivial it is. We have to either handle any such gap in the proof itself or in the exercises. Okay, so this one we are going to do here itself. But how? Again I am going to apply induction, but exactly how? On what variable am I applying induction? We apply induction in fact we see two natural number variables here, right, n and m, but cleverly we can apply induction on n minus m. In this setup you can clearly see that n minus m, whatever it is, for that of course will depend on what n and m actually are, but no matter the situation, n minus m is a positive natural number or a positive integer. So our induction starts from the value 1 when n minus m is equal to 1, we have an. So our aim is to show that an is greater than am. So if n minus m is 1, then n is m plus 1, but that by the definition of our sequence is am plus m plus 1. Now m being a natural number can be 0, that is the least m can be, but we have plus 1. So after all, with am we are adding a positive natural number. So that's why this thing is strictly greater than am. And this is the basis for our induction, because in this smallest possible case where n minus m is taking the smallest possible value, we have in fact shown that am is greater than am. Note one more thing, that here we are not really talking about one or two values of n, or I mean n and m are not fixed. In this base case itself, actually we are looking at infinitely many possibilities for this pair, and these are all the possibilities. Okay, so we have in fact shown something about all such cases. So in this single case itself, actually there are infinitely many cases, but anyway we now have it. So now we have to assume the statement for some k, that is our induction hypothesis. So let an be greater than am for all natural numbers. See, here I am explicitly writing for all n and m, such that in order to show that in this induction hypothesis also there are infinitely many cases involved depending on the actual values of n and m, such that n minus m is equal to k, where k is some positive integer, some arbitrary but fixed positive integer. This is our induction hypothesis. Now let n prime and m prime be natural numbers such that their difference is 1 more, that is k plus 1. N prime minus m prime is k plus 1. Okay, and we have to prove that a n prime is greater than a m prime, that is our aim. Then a n prime of course from this relation it equals a m prime plus k plus 1. Okay, now this equals what? Note that we have to somehow be able to use the induction hypothesis. So induction hypothesis means if we have any two natural numbers n and m such that their difference is k, then for such natural numbers a n is greater than a m. Do we see anything like that here? Of course we see, you can see it here. From this what do we see? From this we see that n prime minus m prime plus 1, if you subtract 1 from both sides, then this is equal to k. So by our induction hypothesis, a n prime should be strictly greater than a m prime plus 1. Okay, so in fact we need not have written this also. Then we can instead write like this. Then a n prime is greater than a m prime plus 1, but we have to be careful. Every step should be logical and rigorous. Is m prime plus 1 a natural number? Yes, it is, because m prime itself is a natural number. So adding 1 will in fact also make it a natural number. Okay, now we can use our definition that we have in the the recursive definition. So according to that, this is a m prime plus m prime plus 1. But like before, this is now greater than a m prime, and that's what we have had to show. And this thing we can write within brackets. Note that n prime and m prime plus 1 are natural numbers such that this in fact allowed us to apply the induction hypothesis and have this first inequality. Thus, by induction, an is strictly increasing. Okay, so we have in fact shown what we wanted to show, or what the author claimed in the text. Now we come to the actual task of showing that A is countable. the set A is countable. So for that we need to define a map. And in the definition of that map, in fact, we are going to use this sequence. That's why we needed it in the first place. Now, we define the function f from, okay, are we going to, let me just see one thing. Have I got it correctly here? Are we no, we are not defining it from n cross n. We are defining it between a and n directly using this sequence. Okay. Because a itself is a subset of n cross n, and we are concerned about its countability. So naturally we would define a map between a and n. Yes. Define a function this by this formula. Any element in A is an ordered pair after all, and our definition is an plus n. Okay, is this definition sound? Is the map well defined? Clearly, n and m are themselves natural numbers, and for a given n, we have a unique natural number an, and that comes from the well-definedness of the recursive definition, the sequence an itself. So an is a unique natural number and m already is a unique natural number, a given natural number. So their sum is a unique natural number. So yes, it is well defined. Clearly, the function f is well defined. Now our main objective would be to show that this f is injective. It's a one-to-one function. We now show that f is injective. This of course we can show in two different but equivalent ways. Either we take two distinct elements in A and show that their f images are distinct, or we take two elements in A whose f images are equal and then show that the elements are equal. So we are going to do the former because the author has done it that way. So let us consider two distinct elements in A. Such that they are different, they are distinct. Now, three cases actually arise. Either the first coordinates are equal, either n is equal to n prime, or n is greater than n prime, or n is less than n prime. Let us consider the case n equal to n prime first, because that is relatively easier. Let n be equal to n prime. Now if the first coordinates are equal, then to maintain this inequality, the second coordinates should not be the same. Then we must have m not equal to m prime. Naturally, this implies that an plus m is not equal to an plus m prime. But because if otherwise if they are equal, you can cancel an from both sides and have m equal to m prime, contradicting this one. Hence f of n comma m, which is an plus m, is not equal to an plus m prime. But because n and n prime are equal, we are under this we are in this case, so this is just an prime plus m prime. But that again, by our definition of the function f is n prime, the f image of n prime comma m prime. So these two images are different when the elements, the inputs are different. Next, so this is one case where n is equal to n prime. Then we look at n greater than n prime. Let n be greater than n prime, keeping in mind that n and n prime are natural numbers, a result that we saw way back when we were studying the system of natural numbers tells us this. Then n prime is greater than or equal to n plus 1. Strict inequality becomes this somewhat more relaxed inequality, but it is maintained. You can have equality or you can still have strict inequality, okay, if this is true. And now with this, what can we get? So now if we look at this, then by definition, of course, this is an prime plus m prime. But because m prime is after all a natural number, so it is greater than or equal to 0, and as such this is greater than or equal to an, okay. But n prime, an prime, but n prime itself is greater than or equal to n plus 1. So in the previous paragraph we proved that our sequence an is strictly increasing. So that increasing nature and this inequality now tells us that this is greater than or equal to an plus 1. And now you again use the definition of our sequence. This is an plus n plus 1. Okay, now we started with f of n prime comma m prime. We somehow need f of n comma m on this side. A part of that we have already got an, but we need m here somehow, maintaining the direction of the inequalities. So what do? We have so far not used one fact, that these n these ordered pairs we are in fact choosing from the set A, which has a condition, right? But since this belongs to A, we of course have this. If you go back to the definition of the set A itself, then you get this. Okay. So this is greater than or equal to an plus n plus 1, but that is now, I think I am missing something here. We need strict inequality. Do I not have that here somewhere, or am I missing something? Maybe I'm overlooking something. N plus 1 is greater than, oh no, it's okay. So n plus 1, because we have plus 1 here, so this is strictly greater than an plus n, if you just forget this one. And now this n is greater than or equal to m, so this is greater than or equal to an plus m, and this finally is, so this thing is strictly greater than this thing. That means they are not equal. That is, again we are getting this same conclusion like this case, that these two things are not equal. So distinct inputs have created distinct outputs. And the remaining case where n prime is less than n is similar, where you just switch the roles of n and n prime, that's all, and you go again proceed similarly like the second case. We thus have this, irrespective of what the situation is, whether n is equal to n prime or less than n prime or greater than n prime, always we are getting the fact that the f images of these two ordered pairs are different. Hence f is injective. Now f is a function with domain A, the set A, and range, the set of natural numbers, and it is injective. Now if we change the range from n, the set of natural numbers, to the image of f itself, I mean the image of A itself, that is the function f from A to f of A is bijective, because already it's injective. I mean the original function we have proved that it's injective. If we change the range, keeping in mind that all the outputs should be there in this new set, then it still remains injective. The injectivity is not affected, but now it is surjective also, because whatever possible natural numbers that were present previously, which were not coming from anything in A by F. Now they have been removed. So it is injective as well as surjective, so it is bijective. And hence A and f of A have the same cardinality because there is the bijection between them, or more loosely speaking, they have the same size. But f of A is not just any arbitrary set. Its special thing about it is that it's a subset of the set of natural numbers, and we have already seen that any such subset is at most countable. Either it's finite or it is countable. Is at most what is that result? Have I written it here? Corollary 816. So naturally A is also at most countable. Hence A is also at most countable, but this is not quite the thing we want. We want A to be countable. That means we have to somehow now make sure that A is infinite. But you go back to the definition of A, you will see that A is infinite. But since A is infinite, we finally conclude and here the proof ends. If you still find it difficult to see why A is infinite, you once again recall the definition of A. To show that this set is infinite, it's also enough to show that this set has an infinite subset whose own infiniteness is easier to see than this one, and you can of course consider these elements in this set, or you can just simply take these. And so on. All of them are okay, wait, no, this is not the I have in fact written the exact opposite thing, because m needs to be less than or equal to n. So if you want, you can take 0, 0 also. Such elements are all in A, because n is greater than or equal to m. Here m is constantly 0, and you can clearly see that these form an infinite subset of A, so A must also be infinite. So we have now proved that this particular set A is countable, but how is it going to help us? That now we are going to see in this next corollary. And this is the corollary, the set this Cartesian product itself is countable. Now that we have the lemma with us, it's not difficult to prove. We have, okay, let me write like this: by lemma 8.1.12 the following set is countable. That is our A. But then the following set is also countable. It's another set, similar one but different. B. Here we just consider the other inequality. We change interchange n and n. It's a different set, of course. There will be some common elements, but it's after all different. A and B are not the same thing. This is because the function f from A to B given by f of n comma m equal to, here also we interchange n and m. Is the bijection. Now this part I am not going to prove. Actually we have been asked to prove this. The author asks why. So we need to supply the details. But I am leaving this, it's not a gap because I am leaving this to you. See, there are many things to prove here. I mean quite a few things. First of all, you need to notice that f is well defined. That itself has two parts. The first thing is that if you are choosing an ordered pair n comma m from A, then m comma n should belong to B. It should be an element in B. that you have to show, keeping in mind that the elements in A, or rather their coordinates, satisfy these inequalities, whereas the coordinates of the elements in B satisfy these inequalities. Okay, so that you have to make sure. Then you have to show that in fact for a given such element from A, this is unique. This is not just an element in B, but it's unique, and that is almost trivial, but still you just do that. That will give you the fact that F is well defined. Then you have to systematically show that F is injective and also surjective. Then only F will be a bijection. So this part I am just simply leaving. Okay, fine. So we already know that A is countable, and now because there is a bijection between A and B, so B is also countable. But what do these two sets have to do with n Cartesian product n? That's because this Cartesian product is the union of A and B. Now, since this is the union of A and B, this is also countable, because we have already seen, although I think we have not proved it yet previously, the result that the union of two countable sets is countable. This we will do in one of the exercises, but we use the result now nevertheless. What is that? It was proposition 8.1.10. This is also countable, and the justification is this. And that's just it. So we have proved that in Cartesian product n is countable. Now there is a more general result than this, which we will not prove now, but we will state it, the next corollary. It states that if two sets x and y are countable, then their Cartesian product is also countable. And for proof, see exercise 8.1. We are going to do these things once we reach the exercises. And now finally, corollary 8.1.15. The set Q of rational numbers is countable. We are now going to take the help of these results that we have proved, and especially this one. Then you may ask, then what is the point of proving the other results that come before this one? That's because in its own proof, we need those results, which we have so far not seen. We are going to see this only when we solve this exercise. Anyway, so let's now see, solution I wrote. Proof. So let's now see its own proof. And the proof, of course, it starts off by considering the set of integers, and we then remove 0 from this set, and then we consider the Cartesian product of the set of integers and that set which you obtain from the set of integers by removing 0. This we do because the rational numbers are quotients of such objects. In the numerator you have an integer, in the denominator you have a non-zero integer. So it goes like this. We know that the set of integers is countable. In fact, we proved this in the previous video, analysis video, but I don't remember the number or whether it's a lemma or theorem. You understand where we are getting this from. So we know that the set Z of integers is countable. This implies this set is also countable. The author asks why, and in fact this can be shown by setting up a one-to-one correspondence between this, and I am going to give an example of such a correspondence. Like this. Note that the function f from this set into this set given by this formula, f of n is equal to n if n is less than 0 and n plus 1 if n is greater than or equal to 0 is a bijection. But this is only a claim, okay? You need to prove that this is a bijection rigorously actually. But if you just draw a little diagram for this whole thing, then it will become clear why. What does this function do? It keeps every negative integer fixed. And you can see that this first list is the list of all integers, and this second list is the list of all non-zero integers. We have not included 0 here. So the negative integers are kept fixed by your f. So this is the function f. This is the arrow diagram for the function. And what does it do with the non-negative integers or the natural numbers? It increases all of them by 1. So 0 is mapped onto 1, 1 onto 2, 2 will be mapped onto 3, and so on. And from this arrow diagram itself, you can in fact see that it's bijective. You can see why it is one-to-one, and in fact you should draw this type of things to be able to in fact write a proof of the fact that this is a bijection, because from this only you will know that, for example, if you want to show that f is surjective, then you will know what the inverse images of the elements that you choose from this range will be under f. Okay, but this whole thing is of course not a part of the proof. It has just simply been mentioned that this is also countable. But then by corollary 8.1.14, yes, so by the one we have not proved today, this Cartesian product is countable. Now consider the map, because I have already mentioned f here, although within brackets, but still, so I cannot write f here, but instead let me just write g. Into the set of rational numbers. Defined by what type of inputs do we have now? They are going to be ordered pairs of integers where the second coordinate is non-zero. Okay. Now, is this map this map in fact need not be, we need not show that this map is one-to-one. It is not one-to-one. Okay, it won't be one-to-one. You can almost see why. For example, g of 1, 2 is going to be the rational number 1 over 2, but that is also equal to g of 2, 4. Now, as ordered pairs or as elements in this Cartesian product, these two ordered pairs are actually not equal. They are of course different. Their first coordinates are different, their second coordinates are different, but the images are thus, there is only one image under G. So the function is not one-to-one, and we don't need it to be one-to-one. The thing is that the domain is countable. That's what matters. So the image of this domain under G will be countable irrespective of what this Q is. So it is going to use one of those results that we saw in the previous video, where I was saying that in this result the range y does not play any role other than the fact that we just need it there. So it's that result, if you can recall. So what I'm now going to next write, it is this: by corollary 819. If you go back to this thing, then you will realize it just says that the image of an at most countable set under any function is also at most countable. By corollary 819, the set The set, or let me write what it actually is, the image is at most countable. Okay, but we know more than the fact that the domain is at most countable. In fact, more precisely, the domain is actually countable. So will this corollary not allow us to say that the image then is countable and not just simply at most countable? Unfortunately, no. It depends on what the function g is. Say you have a countable set. Let me just give you one example. Say you consider this countable set. N is of course by definition countable in a very trivial manner. Now you think of a function f from n to any set y, or for the sake of definiteness, let us take the set of real numbers, say. And what is our function? F of n is by definition say 1. This is a legitimate function, it's a constant function. But what is the image of the domain itself under f? It is the singleton set 1. So although we know that n is countable, it is at most countable, but since it's infinite, it is countable. But this is not countable. This is at most countable, and more specifically, it is finite. So unless we know what type of function we are dealing with, we cannot just simply conclude countability. But luckily, we don't need to conclude. That's because, why I say luckily, not exactly luckily, but we have in fact considered this set not for nothing. We have considered it carefully so that actually this range becomes equal to Q itself, because that's the definition of Q. Rational numbers just look like this, look like quotients of integers where the denominator is non-zero. That in fact is the definition of rational numbers. But since we actually have perhaps I should use another set of brackets. This and this is infinite. So that means this image, if it already we have concluded is at most countable, but now it becomes infinite also. So the image is countable. Hence, the set of rational numbers is countable. And here the proof finally ends. So we have now the fact that the set of rational numbers is countable. And in fact, soon the section itself ends, but with a remark. So I am just going to mention the remark. The remark is this: we know that whenever a set becomes countable, we can use the natural numbers to label the elements of the set, so that we can write its elements like this: a zeroth element, a first element, second element, and so on. The list will never end, but in that list all the elements will be found in precisely one location. So now that we have proved that the set of rational numbers is countable, so its own elements can also be written like this, as a list. And in this list, in fact, every rational number will appear exactly once. Now, we have found this fact indirectly through some results. But if one asks us to actually produce a function that is a bijection, then it's not impossible, but it's a very difficult task. However, we are going to be asked just that in exercise 10 at the end of this section. So this we will do, and in fact we have completed this section. In the next video we are going to start solving the exercises, and eventually we will reach this one, and then we will see how in fact one can set up such a function and show that it is a concrete bijection between n and q. So you may say, after you see that solution to this exercise, that why do we then need to do all these things? That's because these results are somewhat more general in nature. Their only purpose is not to prove the countability of Q, but they have other applications also. Plus they are interesting in their own right. So that's just it. I end things here itself tonight. So the next upload is on Tuesday. So what should we do? Let's do vector spaces. Okay, so that's just it. So see you on Tuesday with vector spaces. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.